Okay, so before the break, we were talking about sort of lead into software, talking about assembly language. As humans, we're never going to make sense of binary. That's just going to confuse us. So there's a step up. There's assembly language, which kind of mixes what humans, things humans would recognize with things machine would recognize. It still probably looks very confusing at this point. Those heading to a 4-year degree, you will either have to take assembly language or assembly language will be an elective. And I would highly recommend taking that elective. Once you get to the point you're ready to take it, machines only do simple things. So it's not a complicated thing once you have enough base knowledge to make sense of what it is. But at this point, that probably looks confusing, which is why I wanted to write an example on the board. Have the same thing written over here in a high level language, which has another layer of abstraction to make it a lot more human friendly. And this is what we'll develop most of our software in, because it's sort of at our level of understanding, not the machines. And the reason I wanted to write this up here, a specific example, which when I copied the example, this was copied from a 32-bit machine. So like this number has another 16 zeros in front of it. Same thing with this number has another 16 zeros in front of it because there's 32 bits in each register that have to be full. But I thought I would leave off the extra 16 zeros when I wrote it down on the board. And these have a bunch. Those are each a numbers, so they each go into their own register. So to fill out a 32-bit register, there's another 28 zeros in front of each one of those numbers. But I thought I would leave off the long string of zeros filling up the board. But you'll notice it looks confusing. And the main thing I wanted to write it up here and point out is that the same thing in a high-level language, what we write when we put together our instructions is very, very different than what the machine's doing. Anytime we have a condition, we'll talk about those briefly here shortly, we're going to write a single word like if, and that'll handle all our conditions. But there are several versions that translates to in assembly language. And really the if that I wrote here translates to a bit that's not written down because it's a discarded bit passing through that circuit board. It's just we have one too many to fit in our registers, so we're going to use that one that doesn't even fit any place we can store it to decide what to do on our jump table and how to hash it when we do it. But what we write is very different than what the machine runs. So I mostly wrote that example up here to express that point and see the differences. We're almost exclusively going to work on this side. Almost all of us. So a lot easier to deal with than that big mess there. I guess part of writing it up here was just to show that it's confusing, but yeah, to show that it's very different than what we will be typing, which does throw some people off sometimes. We might write 5 lines of instructions, and then when we go take measurements, it looks like the machine's only using 30 bits. Or we might write one line instruction, and when we go to run it and take some measurements, it looks like the machine's using almost a kilobyte. So what we write in our instructions is very different than what the machine's running, is the main point there. So as we move into talking about software, in particular software development, the programming languages are, there's different ways we can categorize them. Categorize high-level languages. I'm going to abbreviate that. Categorize our high-level languages. And they're mostly binary categorizations. So sort of one or the other. The first one is our language could be either interpreted or compiled. In both cases, we'll put together our text file. I'll write that here. So we have a text file where we write up all the instructions we want the computer to carry out. Has a bunch of different lines. I'll write them like that. And in an interpreted language, it will grab those instructions one at a time and carry them out. So it'll grab the first instruction and translate that into something the machine knows. Whatever it would be, I just made up the binary part there to represent the part we write. It grabs the first line, translates that into something the machine knows, runs that. Then it'll come back and grab the next line, translate that into something the machine knows. Again, I just made up that binary to indicate that. And just do it one line at a time. So with an interpreted language, every time we hit run, the program is going to, the computer is going to start carrying out those instructions. And if there's a problem in there, it'll start carrying out the instructions one at a time and run all the way up until it hits that big problem. With a compiled language, from our perspective, it looks like we kind of start in the same place. We'll put together a text file with a bunch of lines of instructions, but instead of doing it one line at a time, we'll do all of those instructions and make a file, make an entire big long file of something the computer knows how to deal with. I'll just make up some binary code there. So we have to translate what we know, what we put together into something the machine knows in both cases. And do we do it one line at a time as it runs, or do we do the whole thing all at once in advance of running the program? That's our first major categorization, the interpreted languages versus compiled languages. I'm the only one that have to write the entire thing. I didn't leave much space on the board. Well, actually, that's the only one that had pictures with it. So the rest of them I can probably just list out over here. Our next type of categorization will be imperative languages. So an imperative programming language versus a declarative programming language. And in an imperative language, we explain how to carry it out. Explain how to carry out instructions. Versus a declarative language, which is just which instruction to carry out. Oh, I got to abbreviate. Which instruction to carry out. Which those words are probably hard to follow. The imperative explaining how to do it, that's what you probably think of with programming. So like the Python programming language that we're going to look at in a few minutes, where we say, okay, we're going to store a variable, and then we're going to do some math with that variable and some other data that we're going to feed in from the input device, and then we're going to check conditions and react to that human input, and explicitly tell the machine how to carry out each particular instruction, everything that could happen. Declarative languages are kind of pre-built. So like last week, that stuff that I was copying and pasting for when we looked at databases, all of those were keywords that the machine already knew what to do with. I typed the word there in the SQL stuff last week. When I typed the word select, the machine already knew how to select data. I didn't have to specify go to this database, look for go to this database and grab the data that's stored on the hard drive and bring that back out. the machine already knew what select was, so it's already defined somewhere before. So in a declarative language, somebody's already put it together with an imperative language, and we just have that short list of keywords to quickly do things. So imperative, some of our most popular ones, so like C++ or Python. What else did I put on the list? Java. Those are some well-known programming languages, the things we would normally think of with programming, like how to do each particular step. Whereas the declarative language is mostly pre-built for us. We have a bunch of pre-built pieces and we just put them together in a different order. So like SQL or HTML. And the labs this week, we're going to take a look at an example of both. One of the labs, there's like two small programs to write. One of them's in Python and the other one's in HTML. And if you already know that, feel free to do more. More is always acceptable in my class. I put it together at the introduction level. I know some of y'all have already had at least the SDev 120 class. Some people probably know a lot more programming than that. I think if you went to Prosser in high school and took all the, learned a whole bunch of programming on both sides here from Amy and Mike over there, then feel free to do more than what those instructions are if you already know it. Actually, please do. Try to learn, right? We're in a learning environment. So just because your knowledge is way beyond what the assignment is, at least in my class, more is always acceptable. So try to push what you know. Try to learn something new. Extend it a little further. But as far as the assignment, it is sort of an introduction to those. A couple other terms that line up nicely with this list. Let me underline the main words here. Our actual vocabulary terms that you might have to answer questions on a quiz about or something. Interpreted versus compiled language, imperative versus declared language, scripting or programming, some words that you probably know from normal English with the role computers play in our society. Scripting or programming languages versus encoding languages. Which is often listed as a different category in places where you'll have to answer quiz questions about it and stuff. But I always like to make sure it's written on a board directly below this list, because scripting and programming is what an imperative language is. What we would think of for scripting and programming is explaining how to carry out instructions. And encoding is more a declarative language. Scripting and programming is perform actions. Our instructions are to perform a set of actions or tasks. And encoding is formatting our data. Format data. How are we going to, we have the data in the hard drive and we have a monitor to spit things back out on. How are we going to make it look nice between the hard drive and the monitor so that humans aren't trying to read a bunch of binary code? If we want to put it in human readable form and add some colors and fonts and make it look really nice and all of that stuff. Some points we're going to talk about later because that's very important in the business world. But different categorizations, and obviously there's a lot of overlap. Like I pointed out, a declarative language is a bunch of keywords that were already put together using an imperative language.
Hey, Chris.
Yes.
Under declarative up there, what does that say? When to what?
Which instruction?
Okay.
Sorry, I had to abbreviate it.
You're good.
INFM. Yeah, so which instruction do we want to carry out? So that's like the database stuff last week. The select instruction or the where instruction were just keywords that the computer already knows how to deal with. or in HTML. I think you've seen a little HTML, right, Macy?
Yes.
Our tags, right? When we put a P tag versus an H1 tag, the computer already knows what to do with those. So the computer already has the instruction. So any other questions? And obviously the list goes on. These are the main categorization terms that you will hear, terminology you will hear. But there are some others, and most of the others are kind of like the scripting programming here. You will have heard the words in English when you encounter those. It'll be like, oh, that's the formal definition of what that word means. But mostly these three binary categorizations. So high-level languages are made up of a short list of keywords and symbols that the interpreter or compiler knows what to do with. The things we can enter from our keyboard so that we're not typing 10110001 directly in the machine. Or back in the early days of computing, you'll often see history cite ENIAC as the first computer in the modern age. That's the one that was the secret World War II project. Very few people knew about it, but it was before somebody came up with the idea to connect a typewriter to the machine to input. So whenever they did programmed ENIAC, they took the machine apart and put it back together differently. So I'm from the school of thought that the computer, what I like to call a computer, is what came after the war, starting with like the Harvard Mark IIIs and the EDVACs instead of the ENIAC. Oh, that reminds me of something I saw in the discussion board. Those early computers, ENIAC, EDVAC, up till about 1952, when you saw a C, if you see a C in the name of those early computers, that stood for calculator. We didn't start using the word computer till later. I just remembered I saw something about that, a comment about that related to that in the discussion board this week. But yeah, the early days, the C stood for calculator because that's what it is. It's a machine that performs calculations. But ENIAC during the war was a secret project. Very few people knew about that. If you wanted to reprogram it, you took it apart and put it back together differently. So it was only working in machine language. And then after the war, they developed assembly language and the high-level languages like we work with today. Things that know stuff closer to symbols we would recognize. Maybe not right off bat, right? If you haven't studied software development, you're probably not going to recognize it at all. It's a foreign language, kind of like if you only speak English and look at something written in German, right? It's a different language. You don't speak it, so you don't know what the symbols mean, but you have the ability to learn that. A similar alphabet, so they don't look that, it doesn't look that foreign. And then that short list of keywords and symbols that the machine, the interpreter or compiler actually knows what to do with, get combined in different sets of instructions that can be stored and ran later as needed. And there's a lot of those pre-built things already ready for us to go. The things that we're most likely to need are already put together. And that's what we think of as a programming language. So still some pre-built stuff. And before we jump into our example, I wanted to actually look at that here on my machine. Does anybody have any questions about those concepts? Sort of introducing this. I'm pretty sure everybody has to take everything that's one module in this class, everybody has to take an entire, at least one course on. Some of y'all, it's going to be your field of study, so you'll take a whole bunch of courses on that and get finer and finer details. So introducing it here. Okay, I don't have any questions, so I don't hear any questions. So I'm going to go ahead and come over here with that last part. We're going to look at the Python programming language this week in the lab, and kind of here in a moment to start looking at stuff. And when we say Python programming language, there's sort of layers even there. Python is like a 4th generation language. So assembly language eventually turned into high level languages. And then those high level languages were used to write better languages. And those high level languages were used to write better high level languages. And there's layers and layers and layers of just improvement over the decades that so Python is like 4 generations into high level language. It's a long way from anything the machine knows. But when we refer to the Python programming language, which I have installed here on my computer, whoops, how did my view change? The programs and Python 3.10. So when we refer to the Python programming language, what we're usually talking about is this folder right here, which is filled with Python scripts. Somebody just already wrote a whole bunch of Python scripts. I think this one's not too bad. So I've opened that up with the text editor. Those who have seen some Python before will recognize a few things here. So using other libraries. So this one automatically uses other scripts that were written. A few keywords, set up some functions. Probably looks like a mess for those who haven't seen Python, but there's a bunch of code already written in Python. So we would consider this part of the Python programming language when we go to write our programs or develop software. Long list of those. There's a very important one down here under K. There it is. There's this file called keyword. Which there's this short list here. Can I make it fit all on the screen? If I maximize it, oh, nope, not quite. If I make that a little bit smaller, it would fit on the screen. But from line 19 to line 53. So what is that? 33 words. There are 33 words that the Python interpreter knows. And everything else is built from those 33 words and a couple of symbols. So this very short list of keywords, and then there's a couple symbols like plus, minus, multiply, or math operations, and colons and indenting are important in the Python language. But a very, very short list of things the interpreter knows, and then that's used to put together lots and lots of Python scripts. Calendar's not so bad to look at. If I open that real quick. I'll open that up with my text editor. And I think I mentioned before, if no matter where you're heading in IT, you're probably going to want to look into a good text editor, because that's how we give instructions to the machine, really, is we type stuff on the keyboard, and those Unicode values the machine can interpret or compile into something it knows how to deal with. So you'll want to look into software that is really nice for handling just that basic Unicode. So things that change color when it recognizes what it's doing, or predictive text is useful. I always turn predictive text off because of classroom examples. That box just gets in the way, but it'll predict the word you're trying to type and things like that. But we take those keywords and just build up something like this. So we'll create a little method that we can call anytime we need it. We can ask it to run. Our term for that's going to be calling this little pre-built segment of code that just takes in any number we feed in and tells us whether or not that's a leap year. We'll just divide it by 4. If it divides by 4 evenly, as long as it doesn't also divide by 100 evenly, or 400 evenly. Oh, unless it divides evenly by 400, then it's a leap year. Up until we get to adjustments for leap seconds and things like that. There are some other things in there, and another one every many thousands of years spread out, but that's accurate enough for most of our purposes. Just a little bit of math on any number we feed in, and the computer can tell us whether or not that year is a leap year. So a nice little introduction there. And sort of the idea is we have a short list of things that the compiler and interpreter would know, and then we build up lots and lots of more complex versions using that short list. And then once we've built up a set of instructions, we can reuse that elsewhere. So we just get layers and layers and layers and layers, and get things that are easier for us to deal with, more natural, a lot of pre-built code. It doesn't seem like it in the classroom sometimes, but sort of a thought is there's no need for the same person to write, or for two people to write the same program. Once one person's wrote it, anybody else that needs it can just copy and paste and run it. So there's no need for multiple people to do the same thing. Doesn't seem like that in the classroom because we're very restricted on time, so we have to kind of organize things in the classroom so that everybody can deal with that. But it's a very active subject. We learn by doing. That's why I was mostly focusing on that example to show that what we write is very different than what the machine runs, and a few vocabulary terms. We're going to learn a lot more by doing this, and that's the labs this week. So we want to see where we're going to do this. And my recommendation, I think it's in the address for one of the labs, but both of them you can do here. If you don't have a text editor or language installed locally, there are cloud-based alternatives. A very nice one to work with is replit.com. It used to be repl.it. That was the original name. And whoever designed it thought that should be pronounced Ripple. I would have gone with Repel myself, but replit.com is a cloud-based integrated development environment. So a text editor with a fancy text editor with a bunch of tools that can help us get some code going. Oh, I didn't think I was signed in here. I wanted to point at some stuff on their homepage before signing in. Let me try my other account. Okay, it doesn't know it. Ripple.it. And you will hear that pronounced differently, but when I dug around and looked it up, the people who originally created it were calling it Ripple, like little ripples in the water in a lake, the surface of a lake or something. But lots of other people have looked at that word and pronounced it differently. So when you first get there, you'll see this and sign up for an account. It's free to use and stuff. Has a lot of the cloud features we would expect. So we can write our code right in the browser, write and run our code right there in the browser. Sort of like working on Google Docs, multiple people can work together, simultaneously work on code. In software development classes, I will often use this to help address questions. Like if people are panicking right before final projects are due or something, and send me a text at 2:30 in the morning, having a panic. It's like, oh, let's jump on Ripple and we'll look at the code together and stuff. Chat rooms, all those things we would expect. All the connecting aspects we get from the cloud in an IDE, integrated and development environment. So there are extra tools to help us write code, and it knows a lot of languages. So down here is a list, and this is not even the full list. So they just started listing out the most common programming languages. That way the Google bots would see that, oh, here's a place that you can code those. So when people search for a cloud IDE, it will trigger on the most popular programming languages, but it knows a whole lot more than this. So it's a really nice one to work with. Just sign up for an account, and yeah, then you can share, multiple people work at once and things like that. In the classroom, we're restricted for time, so we kind of have to write small programs and learn the basics of programming. But in the world at large, programmers have kind of moved beyond those small things. The programmers have moved to really big issues that take a lot of people collaborating for long periods of time to figure out. Which, if you're heading down a software development pathway, that tends to throw a lot of people off when they move from the classroom into the working field, because in the classroom, everything is designed to fit in those very tight time constraints we have. And then in the world at large, when you go out in the working field after graduating, the difficulty level jumps up considerably, because the modern world is, for the most part, has moved to problems that are way too big to fit into a classroom. So if you're heading down software development pathway, just be ready for that transition. Make sure you're looking in, it's like staying up on the field. Make sure you're looking into the current problems software developers are dealing with at some point between graduation and employment. So once you create an account and sign in, you'll see a page like this. I guess this is the start page. There's some social media aspects as well. So you can collaborate with, meet other programmers and stuff. The community aspect. For our purposes here this week, this tab will be very, very useful for you. You'll notice there's a Learn tab. And over here, it just goes right into some tutorials. Drawing images with code, that is something that often doesn't show up in the curriculum of academia, but I think it is a very, very useful way to learn coding, is working in pictures, because then we get that visual representation, and humans are very much a visual species. So drawing images with code, even simple images like stickmen and stuff, will really help develop understanding of it. But you'll see there's all sorts of tutorials and things like this. There's a more tutorials button somewhere. I thought there was. Oh yeah, right down here, see more tutorials and videos and lessons and all sorts of stuff to help get you started on that pathway, built right in here. And okay, we learn by clicking around. It's an active subject, so y'all can, when you go on here, click on some of those different tabs and see what's there. Check the blogs down here, see what other people are writing about. Look and see what sort of community aspects something like this has from other software developers. The thing we need to do though is write a program. So to do that, we want to create a new Ripple or Repel, or however you want to pronounce that word. The original developers were calling it Ripple, like making waves in the water. But lots and lots of people have looked at that word and come up with different ways to pronounce it. But that's what we call the programs we develop on the cloud here. So we just need to create a new one. So I hit create and choose what language we're working in. So your assignments this week, there's one in Python and one in HTML. So you can do both of them right here. I'll open up the HTML before we break off today, and it'll, well, might as well look at that first, because it'll go really quick. And then we'll come back and look at the Python one before we end, because that's probably where you're going to start at. But if you want to do the HTML right here, it'll make up some name. You can rename that if you want to. And I guess I have to get that message out of the way. Close. Okay. So there's a bunch of different tools. Over here on the far left is our files. So we have an HTML file, some JavaScript and CSS that it started off with. And we can run it right here, our code in the middle, and then the output of it over here. So we get different things there. We make changes. So background color, blue. Run that. We see different changes, how it's going to lay out and stuff. So you can do your HTML code right here, your HTML part of the assignment right here, see the results of it. And I think the Python one actually points here. And on both of them, you'll notice there's this invite button. So if you want to, instead of coming over here and downloading the file, where's the download button? Instead of downloading the file, clicking on the ellipsis, downloading the file, renaming that, then uploading it to Ivy Learn, you can just share the link with me. So you can share it with other people. So just come over here to the top right and click that invite button and generate a join link. And it will be perfectly okay if you just copy that link and send that to me, because then I'll still be able to see your code from that community thing. And in general, I think that might be better practice, because then we're doing the sort of thing that we would do with cloud-based tools in the real world, sharing them. We don't download them and send the files every time. Some people do. But in general, if it's on the cloud, we don't have to download them and send them. We can just send the link, the URL, which we'll talk about the web in a couple of weeks. That was one of the main ideas that really made the internet take off, was instead of sending you the data across this network, why don't I just send you the really small thing that tells you where to get the data. And if you want it, you can go get it yourself. And that was one of the core ideas that really made the internet take off from 1989, 1990. I saw a few people mention that in last week's discussion board. There's also a Python assignment this week. You can see this list it's quite long. Python's at the top, so I'll come back to that. C and Java, like C++, Node.js, C#, just something blank. Swift is Apple's proprietary language. So anybody that might want to have aspects of working for Apple one day, I know there's a few Mac people in here. Swift is a language you want to look into. There's a guy in Bloomington that teaches at the Bloomington campus that teaches that regularly. He tries to teach it every year, but I think he only gets enough people to run about every other year. But that's the Apple's proprietary language. Go is one Google has been pushing really hard, a language Google has been pushing. So if your aspirations are to work for Google, it might not hurt to go ahead and start looking into the language that Google's going to want you to use, or Apple's going to want you to use if you're hoping to head that way. You can see I just start scrolling. There's a lot of languages here to learn. Y'all can look through that. Y'all know how to scroll around and scroll through the list and click on things with your mouse. We learn way more by doing stuff anyway, so ready to get into the active part. But when you choose the language, you can change the name, but it'll just generate a name, and then hit create, and you'll get over here. It's a different language than we looked at just a moment ago, but you'll see a lot of the same functionality. All the rest of that loads over here in the upper right is still that invite button. So if you want to, you can just come over here and share it directly with the email, or just generate a link to share it. I'm going to guess that most people in our society these days have encountered the two ways we share things on the cloud at some point. And you'll see that over here we have the files that we're working in. Those have to do with the manifest. Don't worry about those. Yours is up here. Your file will be up here, the one called main.py. Over here on the right is where we run it. either a shell console directly, or we can just see the output of it. But you'll notice on the last example, there was a bunch of code there. We could just hit the run button and things would happen. But here, if we just hit the run button, there's nothing there. There's some words, but it can't even highlight them. Those are like a background image there. But you'll notice that it's a very useful background image because it has a link to just open up some examples to start working with. So if you wanted to say calculate a factorial. A factorial is all the numbers multiplied together up to the numbers. So like factorial 5, what they have here by default is really like 5 times 4 times 3 times 2, then usually times 1, which obviously times 1 doesn't do anything, except that it seems really strange to end that pattern at 2. We just go ahead and count all the way down to 1. So the number we're looking at multiplied by every number until we get down to 1. So here's what some code to do that in Python. One way of coding that in Python would look like. And it's coming on 3 o'clock, so we're going to walk through some specific examples on Python on Thursday. I think that's when our class is. Yeah, Tuesday and Thursday. So on Thursday, we'll kind of walk through some examples explicitly and do stuff. I wanted to make sure and point at this because some of y'all may have seen programming before and want to go ahead and jump in and get started. It's a big, powerful tool that will be incredibly useful for you. So it might be worth it to go ahead and set up an account there on their site. And that's the recommendation for where to type your Python code for this week's assignment. And like we looked at, you will also be able to type your HTML code there and immediately get a preview of it, which that one's kind of obvious because we're in a browser. So obviously the browser can preview the web page in the little thing, but we have all the tools we need to develop and test and debug our code while right there in a cloud-based thing. So the normal cloud things, if you want to just, instead of downloading and upload and then uploading the files, feel free to just share it with me for the submission. That's a more normal way to get me to get the files to me in our world. But it's coming on 3 o'clock. I want to make sure there's time to do stuff, right? It's an active subject we learn by doing. The labs have step-by-step instructions, so you should be okay to walk through those, but we're going to walk through some examples in class on Thursday. If you want to wait till after then, talk about more details, some more background stuff. Probably going to talk about Grace Hopper some as a name worth knowing on Thursday. So if you want to wait till then, but that leaves us like an hour of time to actively do stuff. This is an active subject. We learn by doing. Those labs are there. You probably have other assignments to do. You have that research project coming up at the end of the semester. So there's research to do. And most people take more than one class. So I assume you have some homework there. Please use our time productively until 3:50 when our scheduled block ends. So your schedule should say that this block of time is already reserved for something. So please use it productively, learning IT. I'm going to be sitting here ready to answer questions if anybody has any. I do teach more than this class. So if you have questions in other classes, I may be able to help there as well. Feel free to bring me any questions you have. I'm always happy to help. And please use our time productively. As always, text messages and Ivy Learn messages are the two things that make noise on my phone. I can jump back on a Zoom call in a split-second time. Otherwise, unless somebody had questions, that'll be it for today. Okay.
I have no questions at this time.
Oh, okay, yeah.
Hey, I have a question. So somebody used my topic and you messaged me.
Yes.
So should I pick a different topic now, or do I like change something in that topic?
You'll please pick a different topic.
Okay.
If there's something related to that, that's what I was trying to suggest in that email. There are related things, but please change the main topic. Do you have something in mind?
No, not yet, but I was gonna look at it today.
Okay, there's that long list, and that list is suggestions. So if that looking at that list springs up something else in your mind, let me know what you have in mind.
Okay, I'll text you that. Thank you.
Did you have a question too, Macy?
No, I was saying I didn't. I
Oh,
got some
okay.
stuff to work on though, so.
Okay, so please use our time productively. If you have questions, send them my way. I'm just sitting here waiting for questions. Otherwise, I will see you all on Thursday, and that's going to be an example. We're going to actually code stuff and like follow along examples of coding things on Thursday. Y'all have a good one.
Oh, you too.